Hello and welcome to the NPTEL MOOC on Applied Electromagnetics for Engineers. We now move on to another application. Okay. This time what we are interested is to find the value of an unknown load. Okay. So, this application is where we find the value of unknown load. In all the previous cases we have been given what is the load value and then we manipulated the Smith chart in order to find out other quantities. In this application we do not know what is the load that is given. In fact, that is one of the reasons why we are studying this application, because we want to measure that impedance value. So, I do of course a few measurements. From the measurements will I be able to extract what is the unknown load. This problem usually occurs when you want to perform impedance matching. So, you have a certain component in the chain that is misbehaving. Okay. The load is supposed to be say normalized value of 1 plus J2, but instead it is acting slightly different. So, if you want to pin down what is the exact value of the load so that you can adjust the tuning circuit, the matching network or the tuning circuit, you will have to measure this unknown load. The only problem with measuring loads at very high frequencies is that every piece of wire that you connect to the load will act like a transmission line, right. At low frequencies it is very easy to measure the value of an unknown impedance. I can, for example, if I am working only with the resistive impedances or resistances, then I can put a bridge circuit. Okay. One leg will contain the unknown load or the unknown resistance value, and all the other 3 legs will contain the known values, right. And then we, or at least one of the other one will contain the variable load. So, as I tune the other load, I know I have this unknown load in one leg and I have a variable load in the other leg, and as I tune this load here, at some point the current coming out will be equal to 0. At that point I know whatever the tuned value of the resistance will be, that would be the same as the unknown load. If your load involves inductances and capacitances, you can take the load and then apply a certain voltage, measure the current through the device. You can find out configurations in order to do that one, and from the ratio of V to I you can find out, from the phasor values you can find out what would be the unknown load impedance. Unfortunately, none of these methods can work at high frequencies, because the moment you try to connect any wire or any connection to it, the small connecting lead can act like an inductor, capacitor or a resistor or a very nasty combination of all of this, owing to the transmission line effect. So, how do we solve this problem? How do we measure unknown loads how do we measure unknown loads at high frequencies? Well, in the earlier days this measurement was carried out by a process called a slotted line measurement. So, this is a very famous microwave measurement technique in which you use a calibrated line called as a slot line, slot being just a empty slot or rather a slot in a waveguide. To that slot you actually connect a probe, okay, and then you read the probe actually will be measuring the power, because you would be connecting a crystal detector at the other end, and then you would be having a voltage meter, although it is the voltage but it is actually going to tell you the power meter, okay, power values. So, you connect a probe through the slot and then this slot will be adjustable. So, you have a line which is called as a slotted line, and as you move along this probe will keep picking up different values of the power, and in any case you only care about the power values, because you are only going to look at the magnitude of the voltages, you are not going to look at the sign of the voltages. Okay. So, power will be high, voltage is high, power is low, voltage is low. So, you keep moving along measuring the voltage powers, converting the powers into voltages, and eventually constructing a voltage standing wave pattern. You construct a voltage standing wave pattern with the load kept at one end. You have no idea what that load is, but because the measurement is available with you, at this end you have connected the load to the slot line, you simply move the slot line, the probe here, record the power, voltage and do all that and measure the voltage standing wave pattern. Life would have been very simple if this was the only measurement that you needed to do. Unfortunately, the load that you connect, the minima that is produced by a load that is not exactly the short circuit or an open circuit will actually create a problem, because the values of V min and V max that you obtain will not be sharply defined. Okay. I will draw a few pictures to show you what it would look like, but it will not be sharply defined. Okay. But if you want to measure these distances, you know that even a small change in 0.0 0 1 lambda can actually move a large distance on the Smith chart, and hence the values could change in a large way. You want to be minimizing that mistake. Therefore, you want a very sharp nulls or the sharp voltage minima. Okay. To obtain sharp voltage minima, you have two options. You either open circuit the other end of the slot line, okay, by removing the load, you open circuit it. But open circuit has its problems because it normally radiates, okay. You do not prefer to have an open circuited outputs there, okay. Instead of an open circuit, you can short, and if you have a short which is very nice, it could be normally an inductive short, you will produce reasonably sharp nulls along the line. So, as before, the slotted line is here, you pick a short here or put a short at the end, and then you move, measure the voltages, you will be able to find out the voltage minima values. Why am I telling you that it is only voltage minima? It turns out that the minima are much more sharper, right, than the maxima. So, the measurements that you will make with minima are much more reliable than the measurements that you make with maxima. So, for these reasons you would tend to use short loads and measure only the minima. So, what is the advantage of doing this shorted load? What this shorted load does to you is to establish a reference plane. From the reference plane, you find out what is the position of the voltage minima, and the distance between those two should be the distance through which you are going to move on the Smith chart in order to find the unknown impedance value. Let me illustrate this by a few pictures. Suppose I start with the transmission line whose characteristic impedance Z0 I know, okay, and then connect this unknown load to it. Okay. I connect this unknown load and I actually have a scale. So, usually on the slotted line I will have a scale, okay. So, I have these readings. So, this scale is not very nice, but please excuse the scales, okay. So, I have a scale which might go all the way up to this side. So, I do not, okay. So, this is the scale that I have. Usually it will have some 0 marking at one particular point and then go. Please note that the scale 0 is not the same as load location, okay. Mathematically we keep saying that Z equal to 0 is the load location, but on the scale that I have is not the load location. In fact, it would be usually slightly away from the load, okay. On this load with an unknown one that I have connected, what do I observe? Let us say I observe a voltage that looks like this, okay. So, on this scale, let us say I look at the voltage on this way, okay. So, this is my voltage standing wave pattern that I have found, okay. So, this is the minima. So, minima occurred at minus 41. Let us also assume 240 mm is the wavelength, okay. So, 240 plus 41, or rather 240 is the wavelength. So, 240 by 2, that is 120, 120 plus 41 is about 161. Then the next minima occurred at minus 161 and so on. This scale is in millimeters, okay. So, this is what I have measured on the transmission line using my slotted line or the slot line equipment, okay. Now, what I do is I replace this load by short circuit, okay. I replace this load by short circuit, and when I do that I find this type of a voltage measurement, okay. These nulls are fairly well defined, okay, and I can pick any null that I want as my load. I can pick this null maybe, for example, which is located at minus 1. Of course, the next null must occur at minus 1, minus 120, that is minus 121. So, this must occur at minus 121 mm and so on, right. Again one more at minus 121, minus 120, that would be minus 241. So, I will again have this one more minima at minus 241. So, these are the different locations with a short circuit that I am able to find the minima, right. Now, you observe here, if I take this as my reference plane, okay, if I take this as my reference plane, what is this minus 41 telling me? This is the reference plane which will now act as the load, okay, and the minima now with the unknown load is occurring at 40 mm away from the load. 40 mm is the actual physical value. In terms of lambda, that would be 40 divided by 240 lambda units, okay. So, what we are finding is about 4 by 24 or 1 by 6 units of lambda away from the load. we have a voltage minima. This is the first voltage minima that I have. Okay, I have arbitrarily chosen this as -1. If I wanted, I can choose this as a reference, then my minima would be at -161, which incidentally is again 40 mm away, because these are all of course periodic. Now what is the value of this, what is the usefulness of this 1/6? Now here is where our Smith chart will help us. Okay, let us look at the Smith chart construction done very hastily. So this is the Smith chart, I am not interested in anything else. Now with the unknown load, I can also measure what is Vmax and measure what is Vmin, therefore find out the standing wave ratio to be Vmax by Vmin. Okay, and someone has also already done this measurement and given to me the value of SWR. So what I do is I actually draw a circle which I would call as the SWR circle. So in this case maybe SWR is equal to 1 or maybe 1.5, it does not matter what SWR is. You please, in the next examples that I will discuss, I will actually give you the values in order to find this out. So SWR is some 1.5 let us say, and I know that the minima always occurs on the left side of the axis, right, on the horizontal axis. On the left side of this Smith chart is where I have a voltage minima. So which means this should be the voltage minima on the SWR circle. The impedance can lie anywhere over here, but this is where we have landed on the minima. Now from the minima, instead of going towards the generator, if I start traveling towards the load, right, if I start traveling towards the load and reach this point -1, which happens to be the reference plane or the load plane to me, then I would have ended up at the load point, right. So I actually start traveling towards the load. Please remember that you travel this way for the generator, that is clockwise, and you travel anti-clockwise in order to go to the load. So I keep moving in the load a distance of about 1/6, and let us say I landed at this point. Now all I have to do is draw this arc or draw this length, read the values of this one, and then I would have known the normalized value. If I want to unnormalize it, I simply multiply by Z0. In case you do not know where to land on here, you have a scale called as WTL scale. You on the WTL scale you find out this point, which is the voltage minima point, call it as A prime. To this A prime add 1/6 in terms of lambda, right. So point A prime plus 1/6 in terms of lambda you add, okay, and then move to that distance and then draw a line. So this point you would call as B prime. From B prime you move towards the center by drawing a line, and point where you intersect this SWR circle will be the normalized value of the impedance, and then you can unnormalize this value. Okay, so this is very widely used or used to be used. Modern way of finding impedances, and which is much more accurate than the simple slot line measurement that we have considered, is what is called as the vector network analyzer. But to explain the concept behind vector network analyzer is not possible in this course. If you ever take a microwave course, then you will be knowing what is a vector network analyzer. You will know what is the construction of a vector network analyzer. Okay. We finally consider one very interesting application. Okay. This application of the Smith chart, maybe I do not know the number, maybe we are in the 5th number here. Okay. Find the unknown load which we do not know, but someone has measured the value of the reflection coefficient and found that the value of reflection coefficient is actually greater than 1. Well, in the last few modules I have been telling you that magnitude of gamma L can never exceed 1 except under one circumstance. What is the circumstance? Magnitude of gamma L greater than 1 immediately implies that resistance is negative, right. Resistance is negative. The real part of the load that you are considering will become less than 0, and this is actually the case for active or gain devices, right, we have talked about. How do we find out the impedance? There is one simple way, is to use what is called as the negative resistance chart, which was again developed by Smith himself. Okay, and this negative resistance chart actually completes some of these circles. Okay, so the arcs that we are drawing, it will complete some of these arcs, and then it will give you the negative resistance circles over here. It does not matter now that your gamma L is at this point. If you find this chart, you will be able to find out what is the corresponding impedance. Unfortunately, this negative resistance chart is slightly confusing if you are not designing the amplification or amplifiers. So, what our usual method is to use the existing standard Smith chart itself and try to find out what is the value of the unknown load. And the idea is very simple. We know that the relationship that exists between gamma and Z bar being the normalized impedance. What is the relationship between these two? Well, I know that gamma is given by Z bar minus 1 divided by Z bar plus 1, right. Someone has given me the value of gamma L here, which is greater than 1, no matter. So, I can write down this gamma L here, call this as ZL bar and ZL bar, okay, with the value of reflection coefficient expressed in the form of polar form. So, I have gamma L and an angle which I will use a different notation called theta. So, on the standard Smith chart, this would lie somewhere over here. I mean, it will not be on the standard Smith chart, it would actually be lying outside, but do not worry about this. Okay. From the center of the chart, I can draw a line. This angle is theta. The length here will be magnitude of gamma L, okay, and at an angle of theta. I also know that the normalized value of the impedance here will be of the form minus R plus jx. It could be minus jx also, but I am considering here as plus jx, and I know that R has to be negative, correct. So, I can substitute that minus R plus jx into this equation and obtain something like this. So, minus R plus jx minus 1 divided by minus R plus jx plus 1. Okay. R of course has to be positive because we have already taken the sign negative over here. So, let me simplify this. What I now consider is an interesting thing. Let me consider what is 1 by gamma L. 1 by gamma L will be equal to minus R plus jx plus 1 because it goes onto the numerator and this fellow goes to the denominator, right. And what will happen to this gamma L and an angle theta? That will become 1 by magnitude gamma L at an angle of minus theta, which is okay. Now, I do one more thing, I conjugate this, right. So, when I conjugate, I have to conjugate everywhere. Magnitude does not matter what we conjugate, but the angle minus theta now becomes plus theta. Where is plus theta? Which is on the same line. But now, what is the magnitude that you need to consider? That is 1 by magnitude gamma L. So, let us say that is this value corresponding to this magnitude gamma L. This is 1 by magnitude gamma L. So, let us say this is that length that I am considering and it lies exactly on the angle theta. But what happened to this quantity? Well, let us expand this quantity here, okay, and see if what can be simplified. By taking the complex conjugate, the sign of this plus jx will become minus jx, right. So, I will get minus R minus jx plus 1 divided by minus R minus jx minus 1. If I take this minus 1 as a common factor everywhere in the denominator, so I can replace minus values here by plus values, correct, and that minus 1 in here when it goes and gets multiplied becomes plus here, and the plus sign to the plus 1 value will become minus 1. So, let me also remove this plus here, understanding that R is always positive here because we have already done that here. So, but what is this quantity? If I put brackets around, you will be able to easily recognize that what is this quantity. This is simply nothing but some impedance normalized, right, some ZL bar prime minus 1 divided by ZL bar prime plus 1. So, here what we have is a correspondence of some ZL prime with 1 by gamma L complex conjugate, right. So, what you do now? Find out the corresponding value of constant R and constant X circles, find out the value of ZL bar prime here, okay. So, from this from this point which we will call as point A, find out what is ZL bar. Once you have found ZL bar, you simply replace, right. So, once you found ZL bar, which will be some R plus jx, if you want you can unnormalize this by multiplying with Z0, okay, and then you simply replace R by minus R here, so that you obtain minus R plus jx into Z0, which is the correct value of the unknown load impedance. So, this is how you can actually use the standard Smith chart in order to find out the unknown load value even when mod gamma L is greater than 1. One notable point about all these applications that we have developed is that all this development has happened with lossless transmission line. The calculations with lossy transmission line is slightly complicated, and unfortunately we will not consider that lossy line transformations using Smith chart. It is possible to use Smith chart calculations, but they are slightly more tedious. We will not be able to do that one in this course. Okay. And one final point, the values that you obtain with Smith chart are reasonably accurate, but if you want to design real systems using Smith chart, it is not advisable, but Smith chart helps you in visualizing what is happening to the impedance as you move through different connections. So, the value of Smith chart is not in actual values that you will find, which is reasonable accuracy only, but if you want better accuracy, you will have to plug in the equations, you will have to solve those equations, write a code maybe if you want. You do not rely on Smith chart, but if you want to understand what is happening graphically, how the impedance is changing, how the voltage, what is happening to magnitude of gamma, how the angle is changing. So, all those manipulations through different elements become very easy when you use Smith chart. Thank you very much.